శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ 2008 లో స్థాపించిన కళాశాలలో MBA, NAC A గ్రేడ్ మరియు ISO సర్టిఫికేషన్ సాధించిన మొట్టమొదటి కళాశాల శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ త్వరలో అటానమస్ కాబోతోంది.
2014లో ISO గుర్తింపు, 2015లో రాష్ట్ర ప్రభుత్వంచే A గ్రేడ్, 2016లో NAC A గ్రేడ్, ఇప్పుడు NBA సాధించిన సంస్థ శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్
we will be discussing today. I will give a brief introduction to signals and how they are used as part of a VHDL design. Then we look at two styles of modeling concurrent statements where we can specify them behaviorally. We would see the when-else statement and the with select statement and see what hardware both these statements model. As part of this course, I will encourage you to always think hardware, because this is an HDL, which is hardware description language. So please think hardware. So signals are used inside a design. For outside, we have the entity where I can specify my ports, but for inside, I will use signals. We will use signals to represent wires within a circuit. For example, the syntax is as follows. It is written inside the architecture. Between architecture and begin, this is where you will do your signal declaration like this. The keyword is signal, the name of the signal, AB temp, colon, and the data type. In a previous lecture, we saw the different data types: bit, boolean, standard logic. The most common data type used for signals is the std_logic, and then I have some concurrent statements such as temp is assigned A and B. So in hardware you would actually get a signal temp, which would be the output of A ANDed with B, and if I write C is assigns temp and D, so I will get an output C, which would then have temp and D. Again, please understand that these are just signals. Now, if I have to make this a part of a full design, then I have to make sure that this design has an entity, obviously, otherwise there is no architecture. Without an entity, there is no architecture. Then what I would do is I would specify ports, uppercase A, let's just call it X. I would say Y, and then I would say Z, and this output would be O. So X, Y, Z, and O would be a part of my entity, but A, B, temp, and C would be a part of my signals. Of course, then I would also have to write that O is assigned C, A is assigned X, and B is assigned Y. All of these three statements will also be a part of my design, but I just explained to you an example that signals are used as internal connections and they are typically used to communicate changes in your design, and can also be used, you can also use signals to connect larger designs. So for example, if I have a half adder and if I would like to connect it to another half adder, I can specify these half adders as components and I can connect these components using signals. So I hope that this basic introduction on signals is clear, because we will be using these signals very often. So let's move on to the next concept, which is concurrent statements. Concurrent means at the same time, or you can say in parallel. We will look at what concurrent statements mean in hardware, and then we will move on to our statements, that is the when else and the with select statements. So let's take an example. Suppose in C language or C++ or any other programming language, if I write x is equal to x plus y, and let's say x is 3, y is 4, then we all know that 3 gets added to 4 and is stored in x, so now your x is 7. In effect, if x is 3, y is 4, the result here is 7, which then gets stored back into x after some delay, and now this value is 7. But to store it, your computer gives you a register when written in software. However, if you write this in VHDL or in any HDL for hardware, which is digital hardware, there is a small problem that in concurrent statements, there are no implied registers, implied as in by default or as it is, there are no registers. So effectively what you have is you just have an adder whose output is feeding back into its input. This in digital design is called combinational feedback. When you have a combinational logic in between, and you try and feed the output back to one of its own inputs, you cause combinational feedback, and this is a very bad style of design. And I would go to the extent of saying that it is a sin in hardware design to not do combinational feedback where the output of a combinational circuit feeds back into here, because you think, now let's say x is 3, y is 4, then immediately this output will be 7, and now it's 7, then it's 11. You don't know when it's going to stop. It'll keep running in circles. And that is why you will never get a constant, faithful value, and hence you should avoid combinational feedback. Well, then the question in your mind must be that how do I solve this problem? We will see this in a future lecture, but I'll just give you a brief preview that you would insert a storage element or a register which will store the value, and then you can decide when you want to store this new value here so that you don't keep running around in circles. So this we will see when we will learn clocks and registers. So again, combinational feedback is a sin. Do not do this, please. In a previous lecture, I had given a brief intro to the concept of drivers. When I write an assignment statement like this, that Z is assigned A, my A becomes the driver and will drive the value of Z. So, one concurrent statement assignment produces one driver. I hope that is clear. That when you do signal assignment statements, in effect what you do is you create a driver here, and that is when we will again create hardware. This course is all about hardware, so we always need to understand what the hardware is going to be. So let's look at a potential problem. You have a design which is written as follows. Signals are defined as Z, A, B, C, D of the type standard logic, such that Z is assigned A and B. Z is also assigned C and D. So there are what we call as multiple drivers, and now Z here is, I would like to use the word confused, because should I take A and B or should I take C or D, C and D? Well, this is called a multiple drive problem, and this is again a wrong style of designing, because you have to decide how will Z get its value. So the question is, how do we solve it? That brings us to something that we call as conditional assignments. That is, how do we assign the values conditionally? So that brings us to our first problem, which is the when statement. Before that, let me just quickly highlight this issue. We know that signals with multiple sources can be found on numerous applications, like the computer data bus, that the data on the computer, you will receive it from multiple sources. So the same data bus or the data can have different sources, and they could have multiple drivers. But it is your job as a designer to actually decide how and when and why these values are given. Okay? So again, the question is, how do we do that? So let's look at this. The first conditional style of writing conditional assignments is the when else statement. Basically, this is the syntax. Z is assigned A when the signal assigned A is 1, else Z is assigned B when the signal assigned B is 1, else the default value is C. So now let's think what will be the hardware. You would effectively get a series of 2:1 multiplexers. Just a quick reminder of what a multiplexer is, that if I have input A and B and output Y, if my select is 0, then my Y is equal to A, and if my select is 1, then my Y is B. This is a 2:1 multiplexer. So effectively what will happen is, my Z gets my value A if assign A is 1, else my Z would get B if my assign B is 1, else if both are 0, which is the last else condition, then I would get C. Again, I'll repeat. If my assign A is 1, then Z will get A irrespective of what assign B is. So, if assign A is 1, then Z will get A irrespective. It would not care about the value of assign B, and hence this kind of logic is called as priority logic. This means assign A has higher priority combined to assign B, which has higher priority compared to C. So, if I want a situation where A should go through to Z, then assign A needs to be 1. Then I would not care about this value and hence not this value. So again, the when else statement gives you priority logic. Depending on what hardware you want to make, you will decide the right kind of statement. Let's look at another example. Say I want to model a tri-state buffer. A tri-state buffer is basically 3 states that if my input or my control is 1, then my output is equal to input. If my control is 0, then no matter what my input is, my output is always high impedance. High impedance means no current flowing. No current is not zero current, please understand. No current means the current cannot flow at all. So, there is no path for current to flow anywhere. So if I want to model a tri-state buffer using a when else statement, I would say my out1 is equal to in1 when control is equal to 1, else if this is not true, so for example if control is 0, then my out1 would be high impedance, that is Z. Just a quick trivia or a question. So what would be the data type of out1? What would be the data type? I would write signal out1 is of the type standard underscore logic. Now why is that? Because in a previous lecture, remember I said that your standard underscore logic has 0, 1 high impedance. So just a quick point, I thought I'll raise it here. So I hope that the when else statement was clear. Now let's move on to the next statement, which is the with select. Now the when else gives you priority logic, which is if not this then this, so it gives you a priority logic. But if you want parallel logic, that you would like to select either this or this or this, then I would go with the with select statement. The syntax is quite straightforward. With and select are keywords. So with my condition, I select. My target signal would get a first value. Depending on the first value of my condition, it would get a second value if I would have another value for my condition, and then this would continue depending on how many conditions I have. So you first evaluate the choice expression or your condition, and then you compare that to each of these choice values. Now, compared to your when else statement, we will see what's the difference. So for example, if I want to model a 4:1 multiplexer with 2 control lines or select lines, 4 inputs and 1 output, I specify my input and output as signals of type standard logic. I specify my select lines also of type standard logic. Now the syntax for control select is fairly straightforward, which is with my control line I select. So with my control line I select. Z gets A. So Z would get A when my control line, both my control lines are 0, 0. My Z would get B if my control lines are 0, 1. That is, my control 0 is 0 and control 1 is 1. I'm sorry, the other way around. That is, control 0 is 1 and control 1 is 0. My C goes to Z. That is, Z gets C if my control 1 is 1 and control 0 is 0. And last, if my Z would go or get D when both my values are 1. Now the rule is that this is a rule which you must follow, is you have to give a default condition which is when others, because all possible choices you must specify, all possible choices. So suppose if you know only two choices, then the when others clause or when others takes care of this, that all choices must be specified. You cannot have two choices overlapping, so you cannot write, you could not write, for example, like this, that Z would get C when 1, 1 and D when 1, 1. This is not acceptable. So two choices cannot overlap. All choices must be specified. And they must be in a range that can be represented by this control line. So for example, control is a 2-bit representation, so it will go from 0, 0, 0, 1, 1, 0, 1, 1. You cannot write Z is A when control is 0, 0, 0. This will be 3 bits and it is not acceptable because your control is just 2 bits. So I hope these few rules are clear. So let's look at how would you make a multiplexer with a with select, a 2:1 multiplexer. So with your in 1 I would select, your out will get input 2 when my input 1 is 1, which is basically this, else it is 0 when others, basically the other default value. So this is quite straightforward, but it's important to understand what the hardware is going to be. And obviously we will see this in a lab session as well. So the fundamental difference between the when else and with select is that this gives you priority logic, which is a series of parallel or cascade. So this has higher priority over this, and this has higher priority over this. With select gives you parallel logic. Everybody has equal priority. That is because the primary reason is no two choices can overlap and all choices must be enumerated. So if two choices cannot overlap, means it's always going to be just one choice that actually takes place. So hence you will always get parallel logic. So if I have a VHDL design, I can actually if I have a VHDL design, then I can write the architecture define my signals. I can have when else, write it, and then I can have bit select. So you can have a combination of both. Again, if you observe, both these styles of writing statements are behavioral. So I hope that you are now starting to understand the importance of writing behavioral. So this concludes our today's lecture on signals and understanding the concurrent style of hardware, which is when else and with select. In the next lecture, we will look at the sequential style of design and the concept of process.